So now let me run a simulator. I'll use a standard simulator which is already available, that's called as the Turtlesim. It's the simplest simulator. It does absolutely nothing. So this one is not my program, it's a standard simulator, and there you see that there's a robot and this is the simulator. And normally when I run the simulator, I see what is this simulator doing. So I do a ROS topic list, and that's exactly what you see, what this simulator is doing. It has a topic over which you can give the command. If you give any command motion over here, it will start moving. And then this is a weird simulator. Somehow it's publishing pose. So positions can be directly accessed. So it's not a real robot simulator, because if it was a real robotic simulator, the question would have been, how is the pose known when no localization nodes are running? You can check, no localization nodes are running. Nobody is doing localization, but the simulator is giving you pose. So it's a toy simulator where poses are always available. So the simulator is cheating. So I need to give something to the command velocity. So let me look at it. What is it? So ROS topic info command velocity. It takes a message of this type. Currently nobody is publishing to it. Of course, I'll make a publisher, and this simulator is subscribing to it. Let me say what is command velocity. I don't understand it. So I say ROS MSG show. So I'm saying that I don't understand this thing. This topic is dealing with this type of messages. So I say I want more information. So geometry messages, I can just tab and autocomplete. So the geometry messages / twist, it's taking a linear velocity and an angular velocity, and by convention it's taking linear velocity at each one of the three axes. However, the linear velocity is always given in the direction of the motion of the robot, which is x. So the robot is looking here, so this is the robot's x-axis, and even if you try to give a sideways velocity, it will never be read, and if you give a z-axis velocity, that means you ask the robot to fly, it will not happen. And the angular velocity is always rotation across z, so the angular velocity is always given as rotation across z. So let me move this robot. To move this robot, you normally get a joystick control or a keyboard control. This one has a keyboard control. So let me invoke the keyboard control. So I say ROS run. That's again not my program. And I can actually use the arrows to move it. So that's something which is obviously interesting. So let's see what's actually happening. Now I'll not use the So Turtlesim is publishing to command teleop node, which is the one that I created here, is publishing to a command velocity, and the command velocity is going to this simulator. So there are two programs running. The first program running is this simulator, and the second one which is running is this teleoperation. So the teleoperation is giving to this channel, and this channel is giving to the teleoperation node, which is over here, is giving to this topic, and this topic is giving to this simulator. That's what it's going. Let me echo the positions as well. So I say ROS topic echo / turtle1 / the pose were being this thing. So you have the pose at every point of time. If I move the robot, you see the positions changing. And now let me look at the RQT graph. So the teleoperation which is here is giving velocity to a simulator which is here, and the simulator which is here is giving the pose to this utility over here. It's giving the opposed to this utility over here. So that's how all the nodes are talking in the real sense. There's another interesting thing that you could do. That's the RQT plot. The RQT plot can be used to plot any kind of data as it comes. So normally you need a lot of data and the data comes, so you can actually plot in any data. So let's plot in the positions. So currently they are constant, so I'll have to move the robot in order to show you how the positions are changing. So I need too many things at the same time. So that's why in robotics you need multiple screens. So you see the positions are changing, and if you were writing a nice journal paper, these graphs could have been just shown to the publisher. So these are all the graphs, the XY and the theta. So you can study the graphs. It could be a proximity sensor as it travels along. So right now I don't need this, so let me close that up. Now, of course, we've played around with all this, and now what we'll basically be doing is, let me have multiple robots. So I don't think I need the teleoperation. I need ROS server. I also need the simulator. I also need the graph. I don't need to simulate that up over here. Okay, now let's have multiple robots. So there's a service that the simulator provides. So let me look at all the services, which is what I do when I get a new robot. I invoke it by ROS and I say what are the services. So these are standard services, but there's a service which is spawn. And the spawn is a service which will ROS service call. You can actually double tab and you can find out what to do. So let's first call info. Why is there a slash? It's again namespaces. So you see that the robot has every service invoked by it in its own namespace. The simulator has all its service in its own namespace. Everybody has its own namespace. So every service will have a URI, the node which is handling that service, the argument. So I need to give X, Y, theta and name if I need to call in, and the type. So I say a ROS service call spawn, and just double tab, you'll get everything up. Let's keep everything as normal. I specified name as null, so it gave its own name Turtle2. So that's how you spawn the system up. Quickly, nothing is running. Okay, let's move the robot. So this is my first robot. Now the problem was that I had to move the second robot, which is currently out at the corner. You cannot even see it. It's right here at the bottom left corner. So I need to move the second robot. Now the problem is the manufacturer did not give me a code for the second robot. It only gave me for the first robot, or the simulator only has a way to run the first robot. So I said I need to run the second robot, call exactly the same teleoperation, exactly the same code except for rename /turtle1 / command velocity 2 / turtle2 / command velocity. And now you see that I've actually called the program for the first robot and the second robot is moving because I did a remapping. That's what is a remapping. Let me do a ROS topic list. So now you see that Turtle1 is associated with a command velocity and a pose, and Turtle2 is associated with a command velocity and a pose. So there are two turtles and there are two different utilities that they have. There are two different topics that they are associated with. What do I do? Let's create another robot. So, and let's create another one. So I have 4 robots. I should have specified the position, but then in any case, and let me move them up. So I move the third robot and I move the fourth one. And again, if I do a ROS topic list, you'll see 1, 2, 3, 4 robots with the topic. If I write in here, the first robot will move. If I write in this topic, the second robot will move. If I write in this topic, the third robot will move. If I write in this topic, the fourth robot will move. Now I already have a program prepared, and therefore let me just run that program up. So that's a normal PID controller. Now I'm listening to the poses and I'm dealing with transfer of data of this data type. So that it's a P controller, to make it simple. And it's object oriented, so there's a class. I needed a class because a node is acting as a publisher and subscriber both. So this C++ class has, of course, the node handler. If I need to write down the speeds, which is what my controller does, my controller gives output as speeds and gets its input as 2 things, the pose and the goal. So these are the inputs which will be subscribed to, and this is the output which will be published to. And this is the channel or the topic over which the input will come, and this will be used to store the actual input. So that's how a PID controller will work, and every subscriber will have its own callback function. So if a data comes to pose, this will automatically get called. If the data comes to goal, this will automatically get called. And that's my constructor. And what this constructor does is, of course, the only thing that it does is it advertises the publisher and it registers the subscriber. That's the only thing that you do. You advertise the publisher, you get the subscriber, and then I set in goal as something random. I randomly set the goal. So whenever a goal comes, I overwrite my goal class attribute, and whenever the position comes, then of course I write down the position attribute. And one thing that I do is that I control, my main logic is here, the PID control. So if the goal is valid, because I had initialized it to -1 over here, something invalid, then my linear velocity is proportional to the distance. So I calculate the distance here and I set my linear velocity proportional to the distance, and my angular velocity is proportional to the angular error, which is theta desired as a tan 2 goal position minus my position and my current theta, and then of course I limit it to -pi to pi, and that's my angular speed. So I have a linear speed and angular speed. However, it's in my format. So I take the message of the specific type over which I can write, and I set the linear speed as x because the robot's heading direction is always x, and the robot doesn't move sideways. Whatever you write is not important. Robot cannot fly, so only x is important, and robot can only turn across z. It cannot turn across the other axis. So it cannot do like this and like this. It can only turn across Z. So the angular speed is equal to Z, and I just publish it up. Now in my main program, there's nothing that I have to do except for handling the mappings and creating an object of this class which does everything, and just ensuring that my program never terminates. That's spin. And that's what I do. So if I need to compile it up, let's go again to the root. Cat can make, and so devil/setup.sh. Normally my devil/setup.sh will be at the .bash rc always. Okay, let's do that now. Now I really cannot run this up because of the fact that, let's run it up and see what happens. So I say ROS run, package name, example2, and I have no idea what did I call it. I call it as a turtle mover. So to understand what happens, let's look at this thing. So the turtle mover is actually expecting input at goal, but then no goal has been published. And because no goal has been published, this really cannot move. And therefore, let us try to at least give it a goal. In fact, let me run this thing again. So I call up this program that my P controller, so example 2, I renamed the pose because it was taking input as any general pose, and I want the input as /turtle1/pose, and it was writing the speeds to any general /command velocity. I want to rename it to /turtle1/command velocity. I run this thing up, and then I look at the RQT graph. So there is a tele operation which is running. I don't need that, sorry. Yeah. So this is my program, Turtle Mover, and it's writing down the command velocity that's going to the simulator, and the simulator is giving pose to this program that I have written. The only problem is this program also takes goal as input. So let's give the goal as 8,1. I'm not sure which position it is, but then I just gave goal as this position. And let me see what goes happen. And so I mean, it's trying to move using a P controller at a position 8, which is somewhere around here, and a 1, which is somewhere around here, so it does reach. Let me change the goal to 1,8, and yeah, so it goes 1,8. It slows down as it reaches near to the goal. That's because it's a P controller, so it's doing as it's expected. And that's what is the RQT graph. So from a command line, I'm publishing a goal which will soon be another program, and this goal is writing to giving me goal. That's my program. This one is my program. So I'm getting from a command line random name a goal, and the simulator is giving me the pose, and then I write the command velocity, the V and omega, the control, which is given again to the simulator. Now so far so good. So we've done the program. Now let's do one thing. Let's create the standard chaining behavior. I control the first robot. So let's exit this program. I control the first robot. The second robot tries to go to the first. The third tries to go to the second. The fourth tries to go to the first. And I do it as a launch file. So that simple launch file. So there are 4 PID controllers which are running. In fact, there are 3. So the first robot goes by keyboard teleoperation. I do that. The second robot goes to the first. The third robot goes to the second. The fourth robot goes to the third. So there are 3 controllers, and I only have one program to control them. So turtle mover, turtle mover, turtle mover. I only have one program to control all of them. So what I do is I do remapping over here. So I remap command velocity to this specific turtle's command velocity, the pose to this specific robot's pose, and the goal of the second robot is the position of the first robot. The goal of the second robot is the position of the first robot. The goal of the third robot is the position of the second robot. The goal of the fourth robot is the position of the third robot. So this thing is ROS run in itself. So it says ROS run this package, this package, this program, and the specific name will be here, otherwise there will be a variable name conflict. This package, this program, the specific name will be here. This package, this program, the specific name will be here. And then you've got the arguments and remappings. There's no program for arguments here, there's only remapping. So let's run this up. I say ROS launch, example 2, and launch turtles, and the first robot, remember, will be teleoperated. So let's teleoperate the first robot, and let me check that the teleoperation is working okay. And yeah, teleoperation is working okay. And now let's run all the other robots. So you see the second robot is trying to follow the third robot is trying to follow the first, and so on and so forth. They're forming a chain. So that's a chaining example. I wrote one PID controller, I wrote one P controller, and by one P controller, I'm running the first one by teleoperation, of course, currently. The second one is following the first, the third is following the second, and the fourth is following the third. Let's come to the RQT graph to see if I get this thing, and that's exactly what you see. That's the controller for the first robot. That's a controller for the first robot. It's a teleoperation. It gives the command velocity of the first robot to the simulator. That's a controller for the second robot. It gives the command velocity of the third robot to the simulator. That's a controller for the second robot. It gives the command velocity to the simulator. That's a controller for the fourth robot. It gives the command velocity to the simulator. Now all of them also deal with pose as an input, or with goal as an input. So the first let's look at pose. So this gives the pose to this gives the pose, the simulator gives the pose to everyone. The simulator gives the pose to robot 3, robot 2, robot 4, not robot 1, because I can actually look at the robot 1, and because I can look at the robot 1, that's why you don't see a pose for the robot 1 is being given. And you can get exactly the same thing from the command line as well. And that's your simulated, and that's the simulation. So that's the simulation. They're all moving each other. It's not collision aware, so eventually they'll end up overlapping each other. It's a dummy simulator, so they are not collision aware.